Welcome back. In our last lesson, we took a little bit of a look at perimeter and area. Again, stuff from grade 9 and 10, and even prior to that, I believe. Today, we're going to start looking at three-dimensional things. So we're going to look at specifically prisms, cylinders, and spheres. I'm going to point out that cylinders are really prisms as well. They're just a specific type of prism, specifically where the ends are circular. And spheres, I threw this one in not because it really fits in with cylinders or prisms, just because it makes more sense to put it in this lesson than the last lesson, and it's kind of its own thing, and it's actually really easy to deal with. So let's start off by just talking about what prisms are, and we'll draw a couple examples of them and take a look at the volumes and surface areas for them. By the way, for surface areas, I don't put a lot of emphasis on this because surface area is really just areas of individual pieces. So every shape that's three-dimensional has multiple sides to it. The sphere is kind of an exception to that because of its curvature, but everything else is just made up of sides. In each side is a shape. It's a rectangle, a triangle, or a circle, and we already know how to find regular areas. Surface area is just putting the different sides together and adding them all up. So the first one, a rectangular prism, better known as a box. I'm going to try and use my mad art skills here, and you'll see why I didn't become an art teacher. But it's going to look something like this. And again, it doesn't have to look exactly this way, but it should look something similar to that. Okay, much like our rectangles in the last lesson, you can call these three sides whatever you want, or the three different lengths. You can call them length, width, and height, which is typical. You can call them A, B, and C, whatever makes you happy. I'm going to call mine length, width, and height, and I'll put little arrows on here just to be clear what it is I'm referring to on each one of those. So something like that. But again, it doesn't matter what you call them as long as it's one dimension times the other dimension, or one dimension, second dimension, third dimension. Volume is what I was jumping into there, is whatever you call those three things, you just multiply them together to find the volume. So length times width times height. And again, change the names if you'd like, doesn't matter. Surface area. So there's 6 sides on a rectangular prism. There's the front and the back, the top and the bottom, and the left and the right. And each of those are in pairs, and the pairs have the exact same areas. So the front has the same area as the back, the top has the same area as the bottom, and the left has the same area as the right. So the surface area total, and some people use SA for surface area. I'm just going to use A because, again, it really is just an area. There's going to be 2 length times widths. That would be, in this case, the bottom and the top. And I'm going to really run out of room on this one because it's a long equation, or at least it's not a hard equation, but it's a long equation. I've got the left and right, which are both length times height. And then I've got the front and the back, which are both width times height. So 3 pairs of rectangles, and each pair has its own little area equation of A times A, whatever those two things are called. Okay, a triangular prism, and I'm doing triangular prism just to kind of mimic our previous lesson on perimeter and area where we did rectangles, triangles, and circles. But I want to be clear that triangular prisms and rectangular prisms, all prisms really are the same thing. They're just 2 identical shapes that have been stretched apart. So in this case, I'm going to try and draw this. This one's usually a little bit messier, but I'll draw a triangle up here. I'll draw something that looks like that. And then another kind of background there to make it 3D looking. So we have a triangular top and a triangular bottom, and then rectangles connecting the two. So we have 3 rectangles that go around the outside. Those are called the lateral sides. And then we have the triangular top and the triangular bottom. And by the way, if we put this triangular prism on its side, you would say, well, but the left and the right sides are triangles then. There is no top to it. And I mean, from an English point of view and looking at it point of view, you're correct. When we talk about specifically the height of prisms, what we're really always talking about, no matter what the orientation is the distance between the two identically shaped ends. Now, in this case, if that's an equilateral triangle, all three rectangles would be the same. If it's isosceles, two of them would be the same. And if it's scalene, all sides are different, then the three rectangles would be different. We're not going to worry about some of them maybe be the same. In this case, it's definitely two triangles that are stretched out. To go back up to the first example with the rectangular prism, something that makes rectangular prisms unique for all types of prisms is that they're actually prisms in 3 dimensions. The top and the bottom are identical, the left and the right are identical, and the front and the back are identical. So it can be thought of as any of those could be thought of as the height. You can switch it around. But with other shapes, the height is always going to be the distance between the identical ends. And then we're going to call the 3 sides of our triangle A, B, and C, kind of the same way that we did for just the triangles back in the last lesson. Okay, the volume of this, and I'm going to actually state this more generically than you'd think. The volume is going to be the area of the end. So let me just kind of make sure. I'm going to refer to that as the end. And likewise, the bottom is also an end. And the volume is just going to be the area of the end times the height. And I could have actually done that one in the very first one too. You don't have to write this on. I'll erase it in just a second. But you can think of the base on this as being width times length. That's the area of the end as well. So it's still area of end times height. When it's a rectangular prism, it's just a little bit easier to think of as length times width times height. And that equation is actually universal. So if we have an end that is, for instance, a pentagon or a hexagon or any random shape, it could look like a gingerbread man. It doesn't matter. As long as we can find its area, the volume will be the area of that end piece times the height. So even though I'm putting it under triangular prism, it actually works for all prisms. The surface area. Now this one in particular, as a triangular prism, has 5 sides to it. It has a top and a bottom that are both triangles, and then it's got 3 rectangular prisms, 3 rectangular sides on it that may or may not have the same length. So as far as the surface area goes, this is going to be 2 times the area of the end. And I'm leaving it generic like that because, again, I could write in specifically that the area of a triangle is base times height over 2. I want to be careful, though, that we really clarify the difference between the height of the end piece, triangle, versus the height of the prism itself. Because there's actually 2 different heights there. If we draw the triangular end, which would look something like this, we could call it A, B, and C, and then this distance here would be the height. So we have 2 heights. One is the height of the end piece, one is the height of the prism. Either way, depending on what kind of triangle is, if it's right angle, it's a little bit easier to solve, whatever. If we can find the area of that triangle, which we can, because we know lots about finding areas of triangles, then it's going to be 2 times the area of the triangle to take care of the top and the bottom. And then it's going to be plus, there's the A side times height, plus the B side times height, plus the C side times height. And each of those is a rectangle, A times H, B times H, C times H. Another way that I prefer to write it when we're not dealing with triangles, we're dealing with other types of prisms, is that I can basically factor out the H there. Actually, let's still make sure we write in 2 times the area of the end. If I factor H out of the remaining 3 terms, I have H times A plus B plus C. But A plus B plus C is actually the perimeter of the triangle. So that's going to be the perimeter of the end times the height. And that's actually, again, a better way to do it. Because again, if we have a shape that is a pentagon or a hexagon or an octagon or any other shape that we have, if we can find its perimeter, we just multiply the perimeter times the height and we get the total surface area of the lateral sides. Then we add on the two ends. All right, now for the cylinder. We're going to see that this is actually the exact same equation again, just now we're throwing in the circle information. So I'll draw my cylinder there. And again, we have the height of the cylinder that goes from there to there. And we're going to have a radius of the end piece, which is a circle. And so our volume is also going to be exactly the same as it was for the other. Area of the end times height. It just happens that the area of a circle is pi r squared. So we do pi r squared times height. Similarly, for the surface area, we have 2 times the area of the end. Oh. Since it's a circle this time, the area of the end is pi r squared. So that's the area of the top and the bottom. And then the lateral side, and we're going to kind of look at this a little bit more in just a moment. But it's going to be kind of the same way it was in the last one, where it's the perimeter of the end times the height. In this case, the perimeter of the end is the circumference of the circle. And the circumference of the circle is 2 pi r. And then we multiply that actually by the height. So it still follows the same equation for all of these. Like every shape of prism will follow that and that. If it's rectangular, we just simplify it a little bit. And if it's a cylinder, we simplify it a little bit with a circle. But the generic ones, the ones that I just highlighted there, that's always the volume of any prism. And that's always the surface area of any prism. All right, finally, we're going to just take a look at the sphere. And I wrote the equations in here because they're the ones that everyone forgets, myself included. If I haven't used them in a while, I often get these mixed up and I didn't want to forget them, so I threw that there. I'm going to draw a diagram of a sphere. I had to make it look more three-dimensional. I'll do this. There we have a ball. And same thing, this thing from the middle to the outside has a radius of r. And spheres are actually kind of boring because literally the only thing that changes one sphere to the next sphere is its radius. So that's really the only variable that we can have in our volume equation. And as it turns out, the volume of a sphere is 4 pi r cubed over 3, and the area of a sphere is just 4 pi r squared. Not much to do with those besides use the equation when you need to. Like I said, there's not a lot of interesting stuff with spheres because literally every sphere is the exact same shape. They just change size slightly. Okay, I'm not going to spend too long on this, but I wanted to have these on your sheet so that you can kind of see them. These are officially in math called nets. I often refer to them as skins because a lot of students know about them as, like, for instance, if you have a player in a video game, you put a skin around it to give it different colors. That's actually how video game characters often work. They have kind of a 3D mesh model. And then what they do is to make characters look different from each other, they just have a two-dimensional, usually JPEG or bitmap or PNG picture that has different kind of paint colors and faces and stuff on it that they wrap around that three-dimensional model. That gives a whole bunch of characters, like basically humans. All humans will go off the same model, but with just different skins or different color schemes around them. So that's really what they are. Something that you wrap around a three-dimensional object to kind of make it up. So basically we're taking each of these three-dimensional shapes and we're pretending we can unfold it to make it flat. And I'm not going to spend too much time here because I think you can justify to yourself why they look like this. So for instance, just as an example, our box here, if we think of this as like the front, and then this is the back, and this is the top, and this is the bottom, and this is the right side, and this is the left side. I realize that it takes a little bit to kind of visualize that since I've labeled letters in the same areas, but you get the idea. And then over here, this might be the top. This is the left, the right, the front, the back, and the bottom. And I also just remembered that I did back and bottom both with B's. Anyway, you get the idea. Likewise with a cylinder, you've got the ends here. So you've got basically circle A and circle B. And then I just want to point out that this one here, this is obviously the height. And if you look around this is the circumference of the circle. So if I unwrap it, this here is the circumference. So that's where we get that the surface area is the area of the ends, 2 times the area of the end, plus 2 pi RH. And likewise on the bottom one, I don't think I'll draw too much on here, but you've got 5 sides. You've got the 3 rectangular sides, call them ABC. And then you've got the 2 triangular ends that go on there. We can call them, I don't know, D and E. Either way, that's all a skin is. So when you're thinking about the surface area of an object, don't try to necessarily think about it in 3 dimensions. Sometimes it helps to kind of break it down to a skin and just say, what are the individual pieces? And then those are all going to be rectangles, triangles, or circles, and find the areas of them. All right, let's jump in and try a couple of examples. So here we have a very straightforward rectangular prism. It asks us to find the volume and surface area. So I'm going to just go over here and write down volume equals. And in this case, volume is super easy. It's just the 3 dimensions multiplied together. Regardless of what you call them, it's going to be 16 times 8 times 6. And if I pull out my trusty calculator, because I don't feel like doing this manually, 16 times 8 times 6 is 768, and this is feet. So feet squared. All right, and then for surface area, which again is just area. You know what, let me put this box around here so I make sure it's clear what that is. Surface area is going to have the front and the back, which are the same. So there's going to be 2 of those, and each of those is going to be 16 by 6. That's the front and the back. And then there's the left and the right, which are both 8 by 6. And then there's the top and the bottom, which are both 16 by 8. And of course, it doesn't matter which order you do those in, as long as they're all there. 16 times 6 times 2 is 192. 8 times 6 times 2 is 96. And 2 times 16 times 8 is definitely not the answer my calculator just gave me. 2 times 16 times 8 is 256. All right, I add those all together and I get a grand total of 544. Everything was measured in feet, so this is going to be in square feet. Not too bad. All right, here we have a can of beans. So that would be a cylinder. We have a circular top, a circular bottom, and then lateral side. It has a diameter of 8 centimeters. Just draw that on there. And a height of 10 centimeters. Now I'm going to point out that we probably also want the radius because that's the variable that we used in most of our equations. But if the diameter is 8, then the radius is 4 centimeters. So the volume of the can, how many beans it can hold. It says in this case to find it in milliliters. This is going to be a little bit of a unit conversion, but if you think back or look back at the first lesson in the unit, you'll notice that a milliliter is the same thing as 1 centimeter squared. 1 centimeter cubed. So really it's just saying find the volume in centimeters cubed, and everything's in centimeters anyway. It just means that our answer will be in milliliters, which is a little bit more common for food and liquid measurements. Okay, so the volume is equal to the area of the end, which is pi r squared, in this case r being 4. And then we multiply that by height, and we get 10. Okay, pi times 4 squared times 10 gives me 502.65 centimeters cubed, but I'm going to actually write milliliters there because I know they're the same thing. Oh, I just realized I wrote plus up here when this should have been equals. 1 milliliter equals a centimeter cubed. Okay, so this can is just over half a liter. And by the time you factor in, usually there's some air gap or something in there, or some slight off. It's probably a half a liter can. All right, how much aluminum is needed to make the can in centimeters squared? Now, we're not specifically told to find the surface area, but it's kind of hinted at there, specifically between being centimeters squared and needing to know how much stuff goes around the outside. So just be aware that in word problems, sometimes we're not asked specifically to find area or volume. We're just hinted at which one it should be based on description. All right, so our area, our surface area, is going to be made up of two ends. Each end is pi r squared. And then, again, I'm just going to kind of draw this out. If we took that can or the label on it anyway and took it off and spread it out, it would look like a rectangle. And then we'd have a circular top and a circular bottom. And that rectangle is going to be 2 pi r wide from here to here. Because again, it has to wrap around the circle when I go, and the circumference of the circle is 2 pi r, and then its height is h. And we know that that is, I wrote 2 pi r, but we know what r is, so I'll put 2 pi times 4, and then we multiply by h, which is the height. Okay, so the area of the ends together, 2 times pi times 4 squared, is 100.53. And the area of the lateral surface is 2 times pi times 4 times 10 is 251.32. And that should give us a grand total of 351.85, I believe, centimeters squared. All right, so there are our final answers for volume and area. And again, at this point, we probably shouldn't be looking back too much to the equations specifically for surface areas, because we know how to do the areas of basic shapes, and all of these break down into just single basic shapes put together. Okay, a relatively boring one. An official NBA-sized basketball has a circumference of 259. That's right, what am I saying? 259, 29.5 inches. Find the volume and surface area of the ball. Okay, both our volume and surface area equations are going to require us to find the radius. We're going to need to know the radius of the ball, but I know that radius is related to circumference. Circumference of a circle is 2 pi r. So now what I can do is take that circumference that I was given, plug it in here, and that means that the radius is just going to be 29.5 divided by 2 pi. So 29.5 divided by 2 divided by pi equals 4.695. We're going to round that off to 4.7 inches. Okay, so we've done actually one of the harder parts. Now we just have to take that and plug it into our equations. So the volume of a sphere is 4 pi r cubed, and I'll just plug in the r as 4.7 divided by 3. By the way, if you take calculus, you can derive the area of a sphere from the area of cylinders just stacked up, where each cylinder gets slightly bigger towards the middle of the ball and then thinner. So it's like stacking pennies almost, or coins of different sizes to make up the total volume. It's actually an interesting thing. But anyway, in this course, we're just going to use the formula. So 4 times pi times 4.7 cubed divided by 3 equals 434.9 inches cubed is roughly what I'm getting. Okay, that wasn't too bad. Again, it's just a matter of you have a formula, use it. The area is 4 pi r squared. It's a little bit interesting to know that if you cut the ball in half, you'd get a circle. You'd have like a circular cut. And it's exactly 4 times the area of that circle that gives the area of the whole ball. Another interesting calculus proof. But again, we'll just punch it into our calculator. Oh, and again, I'll do an extra line. I could have immediately plugged in that the radius was 4.7. All right, so 4 times pi times 4.7 squared is 277.6. And that's inches squared. All right, not too tough. Now let's move along to this thing. And again, this isn't particularly hard. It's just a little bit more tedious. In order to do this, I need to find go back. We're going to start with the volume. In order to find volume, I need the area of the end, and I want to be clear that even though that it's on its sides, the end are the two identical shapes, so the two identical triangles. So the volume equals the area of the end, and the end is just going to be a triangle, which is base times height over 2. And because it's a right angled triangle, the height is already done for us. It's 18. So base times height divided by 2. And again, I'll take a break for a drink because my voice is getting raspy. All right, I'm back sounding like Sinatra. Okay. So we have base times height divided by 2, and I wanted to point out that this is the height of the triangular end that's 18, not the height of the prism, which is actually this 40 here, the height being the distance between the two identical ends. Okay, so volume equals area of the end, which we just wrote down, times the height, which is the distance between ends. Okay, so we throw that into the calculator, 25 times 18 divided by 2 times 40, and we get out an even 9,000 centimeters cubed. Okay, now for surface area. For the surface area, we have 5 sides, so we need to find the areas of the ends. So the area of the triangle, we actually already solved. That was right here. That was the area of the triangular end. So we have 2 of those. And you'll notice that the 2's are going to cancel out. And just because I'm writing out a room, I'm going to go down to the next line. So we have, actually, you know what? I don't have to do that because I'm going to take a shortcut. We're going to use perimeter of the end times the height. So the perimeter of the end would be 18 plus 25 plus whatever this is. And unfortunately, it's not labeled for us. So I'm going to call it X. And luckily, we can go back to a previous unit and figure out how to solve for X. In fact, we can go back to grade 9 if we want, because it's just Pythagorean theorem. So over here, I'm just going to write down X squared equals 18 squared plus 25 squared. 18 squared plus 25 squared gives us 949. And then take the square root of that, and we get 30.8. So there we found the length of X. And then actually, I'm going to just do this as well, kind of at the side to take up less room. The perimeter of the end is just going to be 18 plus 25 plus 30.8, which is 53.8. So you're always welcome to do those little asides, just means less work up in the main body of this. Okay, so the area of those three rectangular sides all together are going to be the perimeter of the end times the height or the distance between them. Distance between the two identical ends, I should say. All right, so 25 times 18, that's 450 total area for the two end triangles. And then the three lateral sides together are going to have an area of 2152 for a grand total of 2,602 centimeters squared. All right, hopefully I didn't goof on anything there. I think my logic was good. I'm hoping I didn't goof on any numbers, which is always a possibility. All right, one more. I think this is the last one. Yep, that's the last one. It has to do with a Toblerone bar. In fact, I looked this up, and this is world's largest Toblerone bar. Now, for those of you who have had a Toblerone bar, you're going to realize that some of what I'm saying is just a little bit fictitious because of the actual shape of the bar inside. It's kind of broken up into all kinds of little pieces with missing parts. But for our purposes, we're going to figure out how much chocolate's inside, assuming that it was like a solid triangular prism of chocolate. Not quite true, but again, for our purposes, it's something we got to kind of pretend. So the largest Toblerone chocolate bar ever made was 30.7 inches long, and by that I mean between the two triangular ends, and has ends that are equilateral triangles with side lengths of 5.04 inches. I realize 5.04 is not a great number to work with, but this is actually real data. I actually found the real largest Toblerone bar, so we're going to use it. First thing we want to do is find the height of the triangular ends of the chocolate bar. So this is actually probably the hardest part. We've got a triangular end here that looks like that. And we have 5.04, 5.04, 5.04. And what we want is the height. Which we can't find directly. So what I'm actually going to do is just redraw that triangle as half a triangle. I'm basically going to redraw it as half of what it was, pretending that that's a right angle triangle. Well, actually, not pretending, it is a right angle triangle. But an equilateral triangle is just two right angle triangles beside each other. And I know that this side length is 5.04. And I know that the side length of the bottom is half of 5.04. So that's 2.52. And then what I can do is find the height there using Pythagorean theorem. So height squared plus 2.52 squared equals 5.04 squared. Got to remember the hypotenuse is the one that's by itself. 2.52 squared is not a pretty number. 6.3504. And then 5.04 squared is 25.4012. Sorry, 4016. Take that, subtract off 6.3504 from both sides. That gives us h squared equals 19.0512. Square root that, and h is equal to 4.36. At least rounded to the closest two decimal places. And since our other two sides are 1 or 2 decimal places, I think this is perfectly accurate. Okay, so how much chocolate could fit inside? Again, we know it's not actually real if you've had Toblerone, but we'll pretend it's chock full of chocolate. No pun intended. So the volume of this whole thing is going to be the area of the end times the height. And again, the height is the distance between the two ends. In this case, the two triangles. So the area of the end, well, the end is a triangle that has a base of 5.04. Again, when we're talking about the end triangle, we're talking about this one, not the right angled one we drew beside it. So base times height, that we calculated as 4.36 divided by 2. So there's the area of the end times the distance between them, which is 30.7 given in the question. Okay, so 5.04 times 4.36 divided by 2 times 30.7 gives us 337.3 cubic inches of chocolate. That's a fair bit of chocolate. Okay, I wanted to point out something here, and that's that I kind of led you to the answer to B by getting you to do A first. So part B, how much chocolate would fit inside, that was actually a very easy equation to do once we knew what the height of the triangle was. And I specifically asked you to find the height of the triangular end in part A. Be aware that in some questions, whether it's in the homework or assignment or test or whatever, anything that I give you, I could jump straight to part B and just say how much chocolate could fit inside. And as part of that calculation, you would have to go back and use some of your trig to find out the height of the triangle. So this one kind of led you to know to do that. But you should be aware that if you're ever asked to find the area of something, you may have to go back and use or put pieces together to find all the missing values that you need. So just be aware that, again, A, I did not have to actually ask separately. It's implied in part B that you're going to need to do that anyway. All right, and then how much cardboard would be needed to cover the bar? I'm going to try and leave as much of that upper stuff on there as I can. The area of cardboard is going to be the two triangular ends. And the good news is we actually calculated the area of an end in part B right here. That was the area of the end triangle. So we're going to have 2 times the area of the end triangles. And those 2's will cancel. And then the perimeter of the whole thing times the height or the distance between the triangular ends. I'm going to do it slightly differently. I know the perimeter is just 3 times 5.04. So rather than write down the perimeter as one single number, that's how to find the perimeter. And then we multiply that by the distance between the ends, the 30.7. Incidentally, the perimeter that we just calculated there makes complete sense because it's 3 identical rectangles, all of which is 5.04 times 30.7. So regardless of how you actually write it, it's going to be the same thing. Okay, so those end pieces are going to be 5.04 times 4.36. That's 21.97. And then the sides are going to give us 3 times 5.04 times 30.7, which is 464.18. And then we'll throw those together and we get 486.15 square inches. And I think it's probably overkill to include 2 decimal places there. It's about 486 inches squared. And again, a little bit fictitious because in real life there's going to need to be a little extra cardboard, so basically parts that you have to like fold and glue and all that stuff. But the actual surface area of this thing's 486.15 inches squared. Okay, I'm going to stop there because there are some practice problems to try. I'm going to point out this first one, you'll notice that doesn't look like a straight up rectangular prism, but if you use your thought process on how shapes work, you can break it into pieces that work out nicely. Here you have a lovely block of cheese, and here you've got some tent to work with. And then there's a few word problems that have no diagrams, like for instance, a can of beans again. So you don't really need a diagram to know what a can of beans looks like. All cylinders look the same. Anyway, give those a shot. Check the answers at the bottom, see how you go. If you're doing fine, fantastic. And if you need a little bit of help, make sure you contact me and let me know you need some assistance. All right, I will see you in the last and final lesson shortly. Have a great day.